Welcome to Lecture 25B, entitled Modeling Using Dirac Distribution Functions. So before I get started, I just want to make a general note here. Usually, what we're going to be looking at are called Dirac delta distributions, but often you also heard as being called Dirac delta functions, and sometimes Dirac functions. But more or less you can essentially say they're more the same, but accurately speaking, it should be a Dirac delta distribution. All right, just keep that in mind. So this material comes from a portion of section 2.1 of Reading Assignment 5. There'll be more discussed in one of the tutorials, but I'll just give you a quick overview. And also some of this material you should have been exposed to in MAT290. Which is concurrently running in the fall term, but to what extent you've looked at it, it's not clear. So the objectives of this lecture are to understand how to apply Dirac delta distributions to model scalar density rho for point, line, and sheet sources. Secondly, understand how to apply Dirac delta distributions to model a flux density J for line and sheet sources. Again, whenever I say flux, it invokes the notion of having to deal with a vector. If I just say density, then that's a scalar, but flux density means, yes, it is a vector. Thirdly, how to calculate the integral of a scalar density and flux density when Dirac delta distributions are invoked. So the concepts, visualization skills are basically how do you model point, line, and sheet sources for irrotational field problems, and how do you model line and sheet sources for source tree problems. And finally, what are the various techniques for computing integrals involving Dirac delta distributions? Sometimes basically it's done in Cartesian coordinates, sometimes in cylindrical coordinates, sometimes in spherical coordinates. And so in the different coordinate systems, the distribution functions take on different forms. As usual, the second slide is just an overview of the slides to follow, so we'll just skip over this one. Okay, so just a little bit more on Dirac distribution functions, more or less for modeling points, lines, or surface sources. So consider a scalar function or vector-valued function which is infinite or undefined at specific points and is zero elsewhere. I mean, that's basically the problem that we're looking at. So in this case, to model such a thing, you cannot use sort of standard functional approaches. You need to invoke distribution functions, or what we call Dirac delta functions, to model the behavior of said function at the specific points in question. All right, in this particular course, we're going to choose distributions which have even symmetry. Why? Makes things easier to calculate. It doesn't have to be even symmetry, but the vast majority of problems that you'll be looking at, you'll find that the distribution functions are even though it's not explicitly stated. Okay, so let's look in more detail at the mathematical representation of distribution functions. So the distribution properties in a limiting process, Dirac distributions have the following unique properties, and I've just stated them here, three of them. We use the symbol delta to describe a Dirac distribution function, or just whatever you want to call it. And there is an infinite number of ways to model it, and depending on the type of problem you're looking at, it may be easier to use one formulation versus another. We'll show such an example shortly. So if we take this delta Dirac function, delta, evaluated at an argument of x minus x prime dx, and integrate from minus infinity to positive infinity, then the property of this function is it gives you the value of 1. The Dirac distribution is infinitely large and has zero width at a specific location in space and is zero elsewhere. So the point at which this problem occurs is when x equals x prime. That's basically what part A is telling us. B, if we have an even symmetry, then if we integrate from minus infinity to x prime, which is the point of contention, and we compare that to integrating from x prime to infinity of the same function, then we find that they're equal to each other and each is equal to 1/2. That's basically because of even symmetry. Clearly, if you integrate from minus infinity to positive infinity, you get 1. All right, so that's something to keep in mind. So, thirdly, if we integrate f of x, some arbitrary function, delta x minus x prime dx, between minus infinity and plus infinity, then what this does is it samples the function at x equals x prime. So the result of this computation is fx prime. That's why it's called a sampler. And I think in MAT290 you'll make reference to this particular property of the Dirac distribution. All right, so just to sort of reiterate, delta of x minus x prime essentially is 0 for x not equal to x prime and undefined for x equals x prime. All right, that's basically how we state it, but the most interesting property is when you do integrals with the Dirac delta distribution. All right, just a couple notes. The limits of integration are shown from minus infinity to plus infinity, but in actual practice, the integration result remains unchanged if you use values that are finite, but at least bracket the peak. So typically, we would choose integration limits that just bracket the peak of the Dirac delta function. I mean, it makes no difference whether it's minus infinity to infinity, or for instance, for part A, you'd be going from a value which is x prime minus delta and x prime plus delta, because in that way you're at least bracketing the problematic point. So let's look at actually an example of a Dirac distribution. The simplest one to use is the Gaussian distribution. If you want to look at this, there's a URL link here available. You can click on it and watch what happens as you vary the value of A. So the Gaussian distribution is basically a limiting process. So in this case, the delta x would be the limit as A approaches 0 of 1 over A square root pi e to the minus x over A squared. You'll notice that this distribution is an even function, which means whether you put x in or minus x, the result is the same, which would mean that the area under the curve for positive x and the area under the curve for negative x is equal. And so this is what we mean by even symmetry. So again, you can play with the value of A with the slider here just to see what happens, that as A gets smaller, this gets narrower and this height gets larger. So if in effect we're mimicking a Dirac delta function with this example as A goes to 0. Okay, so let's look at specific objects such as filaments and cylindrical coordinates and point sources in spherical and polar coordinates. We'll also look at these things in Cartesian coordinates, but in particular be interested to see how they differ when you move to a different coordinate system. So in either cylindrical, spherical, or polar coordinates, the radius r is only defined when it's greater than or equal to 0, and thus integration over r results in only half the distribution being mapped out. So for instance, you'd have basically at theta equals 0, you would see 1/2 of the distribution. At theta equals pi, you would see the other half of the distribution. All right, so that just to keep a note of that you're seeing only half of it. The upper integration bound on R for cylindrical point sources in 2D or 3D, filamentary sources in 3D, or spherical point source in 3D can just be some value slightly larger than 0 in order to capture the Dirac delta function at the origin. So for these cases, we obtain the following general result, that if you take the integral from 0 to some value just ever so slightly greater than 0 of delta r dr, this value is equal to 1/2. Okay, so this is how we would describe things in polar, cylindrical, or spherical coordinates, because we're invoking the notion of an r here. If you're interested and you have time permits, which I doubt will be the case, you can review chapter 3.1 and C.2 of Appendix C in the context of your MAT290 course. This appendix gives more detailed introduction to Dirac delta functions. Okay, so I'm just going to state some results here. Let's look at a pictorial description of the scalar density Dirac delta distribution for rho. And so this would be the example of a point source. And so this is a point source in 3D located at the origin. So if I were to describe this in Cartesian coordinates, then the units of rho would have to have a charge density, and so each one of these would make a contribution of 1 over meter, 1 over meter, and 1 over meter. And so Q has units of coulombs, so all of this would be units of coulombs per cubic meter. So rho takes on this form, but because it's a distribution, that means at a point source you have a delta x, delta y, delta z. This represents the point source. In spherical coordinates, and again you can look this up in the notes, then rho would take on a different form altogether. In this case, rho would be Q delta of r divided by 2 pi r squared. Now, the reason why is this the case is because when you integrate the total charge over volume in spherical coordinates, you need to use r squared. R squared sine phi dr d phi d theta. Here again, I'm not using rho because rho has been used to describe a charge density. So this would be the formulation of the Dirac distribution for a point source in 3D if described in terms of spherical coordinates. All right, here are a couple of other examples. This would be a line source in a Cartesian coordinate. Essentially along the line, there is a functional description, and so there's nothing happening along the z direction. So this lambda basically says charge per unit length along this length. And delta x, delta y means that if you were to do a cross section here and look at the, for instance, if you did a level curve, you basically would see everything basically is confined to the xy plane, and so that's modeled as a two-dimensional Dirac distribution. On the other hand, if you want to describe this in cylindrical coordinates, then this will take on a different form, and this involves 1 over r. Because when you integrate this in cylindrical coordinates, you'll have a factor r dr d theta dz if you want to compute the total charge. So this is where the 1 over r factor occurs. So this would be, say, for an infinite line example. Infinite plane. In the plane, if you go x or y, basically you can describe in terms of a function. And so this would be in units of coulombs per meter squared. This would have units of per meter. And so rho would still be coulombs per cubic meter. But this would be a surface charge density, this sigma value. And of course, change is occurring in the z direction, and occurs at z equals 0. So this would be modeled just as delta z. For an infinite cylinder, where we have basically a surface charge right on the exterior surface at some position r. In this case, we would just represent it in cylindrical coordinates. So in this case, this sigma is a surface charge density in units of coulombs per meter squared. The delta function will have a units of 1 per meter, so the units of rho are still coulombs per cubic meter. But this delta function now is the radius minus capital R, which represents the radius of the cylinder. And so there's only something happening when R equals R. And so this is a representation of surface charge on a cylinder of radius capital R. And for a sphere, it looks exactly the same, except this is now going to be represented in spherical coordinates. And delta r minus r, that means the things of interest are occurring when little r equals capital R. And again, if you look at this basically has units of coulombs per meter squared. This has units of 1 over meter. So this would represent units of coulombs per meters cubed for rho. And so this if we're dealing with spherical coordinates. All right, I've shown here basically a sort of an example of the Gaussian distribution, and you can play with this as well. And so you can toggle these switches to see either the distribution as a whole or a trace. This is a trace, so you can clearly see that this part and this part basically are identical to each other. It has even symmetry. And when you basically play with this A value, you can watch this thing to get smaller in this direction and start to peak in this direction. And so at least you can visualize basically what is happening. All right, so this is just a trace that's taken, this example here. Okay, so Dirac distribution, if it were a surface charge, this is another example. So in this example, basically, you can see that it peaks right at r equals capital R. In this case, the slider B represents the radius r of the cylindrical shell. And so again, by changing A, what you're doing is you're going to force this to get, the width to get smaller, but this thing will start to peak. Now this here is just representing just the trace, but you can also toggle this so you can see the full distribution if you wish. So this is sort of just a sort of a way of picturing the distribution function. All right, so now the next thing to do is to look at the integral properties. That is, if we're working with a Dirac delta distribution and we want to integrate rho, what basically are the calculations that we need to do? We could be looking at units of coulombs per cubic meter for rho, or kilograms per cubic meter for dealing with a mass density. The units of the integrated scalar volume density rho does not depend on whether the function representing rho is continuous, discontinuous, or a Dirac delta distribution. And just to reiterate, the shaded yellow area is actually rho. So you'll notice here that all of these things taken together represent rho. Units would be in terms of coulombs per cubic meter in this example. And just to recall that each one of these represents 1 over meters in terms of units. This is total charge, which is Q, which would be coulombs. So the units of this would be coulombs per meters cubed, which just means it's rho. Similarly here, this taken together would represent rho, and you can show that in fact the units of this would be also in terms of coulombs per meters cubed. You got a meter squared because of the r squared, 1 over meter as a result of delta r. And for each one of these, the same thing. So if it's a point charge, we can either do it in Cartesian coordinates, which means you'd have just delta x, delta y, delta z. If you integrate each of these in turn, their contribution is 1, and so you end up with Q. In this case, we're using the differential volume in spherical coordinates, and under those circumstances, if you integrate this, you'll find that you again will get Q. If we're dealing with a surface, so we could have basically a planar surface, a cylindrical surface, or we could have a spherical surface. So there would be a surface charge density, and a surface charge density. So in this case, sigma would have units of coulombs per meter squared. Delta Z have units of 1 over meter, so still this represents coulombs per cubic meter. If we integrate delta Z dz, that would be equal to 1, so you'd be integrating sigma dy dx to obtain the total Q on the charged planar surface. If it's a cylindrical surface, then this again is coulombs per meter squared, and the actual surface is at when r equals r, so this is now represented as delta r minus r. And in order to capture the total Q, r has to be integrated from 0 to some value r just greater than r to capture the whole thing. And then this is the differential volume in cylindrical coordinates. In spherical coordinates, everything looks the same, except that the differential volume basically takes on a different form. For a line charge, if we're dealing with Cartesian coordinates, and the line basically is in the z direction, in this case in the x direction, and so that means that if you were to do a trace, you'll find that the surface pokes through the yz plane. If you integrate each of these, they give you a contribution of 1, and so then we're just integrating in the x direction, which means you're computing the total charge along the line, which is directed in the x direction. Here's an example. For instance, we do the problem in cylindrical coordinates. In this case, basically, we're dealing with dz, which is basically along the length of the line, and rd theta, which would represent the dy dx you're seeing here. So in this case, again, the limits would be from 0 to some value just slightly larger than 0. And the result of this integration will give you, again, the value of Q, total charge. All right, now let's look at a pictorial description of the vector valued flux density distributions for J. And so in this case, it's a vector. So this example shows, for example, a surface flux density for a planar sheet. J is oriented in the x direction, but it sits only on the sheet. So the way to represent this, the J of S is a surface charge density. That would be in terms of amps per meter. And basically, at z equals 0 is where you have a problem, so this is basically represented as a Dirac distribution. The units of J will be amps per meter squared. If we're looking at a line flux density, the units would be current, I, that appear in front, amp, And if you do a trace, then basically the only differentials of interest would be x, dx, and dy. And so it's two-dimensional. And so delta x, delta y represent the distribution of the current. And the units of J would be amps per meter squared. The units of I would be amps, but each one of these contributes 1 over meter, so that's where you get your meter, 1 over meter squared comes from. In this case, it's in the z hat direction, so I see z hat here. If you were to do this in cylindrical coordinates, then it will look a little bit different. You can see it has a 1 over r factor here. And r basically would only exist for r greater than 0. And so this would be the form that J would take on if you're going to solve a problem in cylindrical coordinates. Again, J is still amps per meter squared. If you have a surface current, and there are two possible examples of a surface current, one where the current is in an axial direction, and the other is when it's a circumferential direction. So in this case, basically, it's a surface current, so this is this Js, which has units of amps per meter, and it's at r minus r, so it means right on the surface, which is when r equals r, and it's in the z hat direction. So if this has units of amps per meter, this has units of 1 over meter, that's consistent with J having units of amps per meter squared. In this case, the current flows in a circumferential direction, which means theta hat. So you can see it's theta hat. Everything else remains the same because essentially the current's basically flowing on this sheet, which occurs when r equals capital R. So this hasn't changed. The only thing that's changed is the direction in which the current flux density is flowing. All right, so calculating a scalar flux from flux density J, there's some guidance. Given a vector value function J and a differential area of the element ds, because we're going to calculate flux, we're taking the dot product of the vector valued function J and the differential surface area element ds. The expression J dot ds is a scalar valued function and represents a differential flux. The orientation of ds with respect to J in Stokes theorem problems is a degree of freedom. So this is where it becomes important because you want to make sure that when you do the integral of J dot ds, you choose an area which makes the integration as simple as possible. So the choice for the shape of the surface area depends on the direction of J. So once you know what J is, because it's a given, you can establish what the surface area vector should be. We typically will choose J to be either parallel to or perpendicular to ds. In this way, the cosine dependency of the angle between the two vectors can be removed, which basically implies the cosine of the angle is either 1 or 0. We'll be looking at how to construct such a surface as we investigate specific problems, namely specific geometries. The units of the integrated flux density J does not depend on whether the function representing J is continuous, discontinuous, or a Dirac delta distribution. We've already shown that to be the case. All right, so now let's consider, for instance, if we're interested in the scalar flux property obtained from the flux density vector J, which means we're integrating over surface area. So the units of the current flux density would be amps per meter squared. And so, for instance, you could also consider a problem which we're dealing with mass, in which case the mass flux density would be in terms of kilograms per second per meter squared. By the way, amps per meter squared can also be written as coulombs per second per meter squared. So let's look at the specific scenarios that we'll be considering. The shaded area, yellow area, is in fact the flux density vector J. And so we have a number of cases to consider. The continuous case for computing the current flux, right, which would be I. We're just integrating J dot ds over the surface of interest. If it's discontinuous, means that you have to basically look at it as a piecewise continuous system. So this would be for one of the regions which is continuous, and this would be for the other region that's continuous if there's a discontinuity between these two regions. If there's a third discontinuity, then there'd be a third integral. As far as a Dirac delta distribution is concerned, if we're dealing with a 3D problem, we can have basically a current on a surface, or we can have a current flowing through a line. So if we're talking about a current through a surface, we've got three cases to consider. A planar, which is basically current flowing along a surface, axial, which means current flowing on the surface of a cylinder along its length, and the current flowing in a circumferential direction around the outer radius of the cylinder. There's 3 different cases. And for line, basically, it's just a line. So let's look at this example if it's a planar. The difference here now is that it's a vector, and so we're taking the dot product between the current flux density vector and the surface area vector. Now, we mentioned earlier that you can choose a surface area vector to make the integral as simple as possible to calculate. And since J is typically given in this example, basically it's a plane that's lying on the xy surface, which means the Dirac delta function is with respect to z, but it's flowing in the x-hat direction. And so the simplest thing to do is to create a surface whose orientation vector is in the x-hat direction, which means its differential surface area magnitude is dz dy. If you compute this calculation, you get the total current, I, and again, regarding the delta z, you just need to integrate slightly above z equals 0 and slightly below to capture basically everything you need. In the case of current flux density flowing on the surface of a cylinder radius r in the axial direction, then clearly it's z-hat direction, and this represents the current flux density along the z-hat direction. So in this case, we would want to pick a surface area whose orientation vector is z-hat, but in cylindrical coordinates, that the area differential area would be r dr d theta. And lastly, if it's in a circumferential direction, then this current basically is in the theta hat direction in cylindrical coordinates. So we want to basically choose a surface area which is oriented in the same direction as the current flux density, which would mean theta hat. In which case we're dealing with a differential surface area magnitude, which is dr dz. Okay? For the case of a line, if we're dealing with Cartesian coordinates, and we have basically a current flowing in the z-hat direction, then this would represent the current flux density, right? And it's along the z, so this could be a potentially a function of z, but typically if symmetry is applied, this is a constant value. And you've got to pick an area vector whose orientation is in the same direction as the current flux density, z-hat, which means its differential surface area is going to be dy dx. And if we do the same problem in cylindrical coordinates, then effectively the differential area in cylindrical coordinates would be r dr d theta. It's still in the z-hat direction, and this would now represent the current flux density, the magnitude of the current flux density in cylindrical coordinates. Is the magnitude. So that concludes Lecture 25B. Thank you for listening.